We should, yeah, it is live now.
All right.
So just one more thing. Let me just, yeah, it's done. Good. Okay, I can see that it's live. Fantastic. So before we get started, let me just kick it off, Pavesh, and then you can take it over. That's
Yeah.
fine.
Yeah.
Let me hit the record button.
Yes.
It's recording. All right. Hey, welcome everyone to this SDE Skills weekly session. In case this is your first time joining and you haven't joined the Slack yet, please make sure that you go to sdeskills.com/Slack. It's a super active community. We've got a bunch of folks. We're doing we're doing this weekly design sessions. We're actually doing daily lead code practice, and we're also engaging in the 30-day lead code challenge as of now. It's generally like super active and super interactive for community. What I would encourage is that if you haven't been an active participant, one of the things that will strongly help you is if you want to just start um, uh, volunteering to present content and things like that. The weekly design session. So this specific thing is the weekly design session. Folks who are looking at it, we cover different topics, and these topics are usually a little more complicated, a little more involved, and it's generally prepared content. Like Union Find is a data structure, so it's not really a design session, but it's kind of design of a data structure in this case. So with that, let me hand it off to Bhavesh. Bhavesh, just quickly introduce yourself, and then we'll get started. Thank you.
Yeah. Hello, everyone. My name is Bhavesh, and welcome to the weekly session. In this weekly session, most of the time we discuss about special topic, and last week we decided to talk about Union Find and its joint set. Before I go into the detail, I would like to know if is everyone comfortable with Union Find. They have done it before, or they haven't heard about it, or this joint set. If you can just put yes or no in comment, that would help me to figure out how much detail we have to go.
Couple of beginners, one no at this point. So it does look like people are in the early stages.
Okay. Okay. All right. I think what I'm figuring out is that either people know it or they are beginner, and they might have heard it or used it or not implemented it, right? So we'll go through the detail about theory, what it is, and then try to implement also, and then we'll see a special use case for this data structure, right? So to begin with, right, let's start with a problem, and then probably we will derive how we can solve it efficiently, right? So the problem, so we know about counting island problem, right, or counting water bodies or pond problem, right, where for example in this kind of so the problem start with this. Would I be able to draw? Okay. Okay. So let's say that we have a problem of ones and 1 and 0, right? That means we have given Okay, and this is two-dimensional array. We are given ones and zeros, and 0 is water and 1 is let's say land. So we have to count the number of pond in this. So can anyone uh, uh, would like to tell me approach how we can count the number of pond in this? That means, for example, this is one pond, and why both are connected. So 0 is water, and we are saying that it can connect in 4 directions. That means left, right, up, and down. So suppose I have another 0 here, that become another pond. Okay, there is another 0 that will be part of the existing pond.
So
yeah.
identify 0 and I plus 1 and I minus 1. So and j plus 1. So check on the j minus 1. Check in all the direction. If it is there, then recurs that particular place, so that you cover the entire area.
Okay. So
You can make
and we
DFS.
will start. Go ahead.
I told that we can make use of DFS to check in all the directions, like whether land is there on up, left, right, bottom.
Right. So basically, we start
And,
from this point and keep finding till we get the 0, and then we do the DFS from there.
yeah.
Right.
Kind of. Yeah. We check whether it is on the boundary or not. Like.
Do we need to? So this middle
DFS
one,
or
right?
BFS?
This one is not in the boundary, right?
DFS.
So this one is not in the boundary, right?
Yeah. This one is not in the boundary. Yeah. Let's say told if 0 is at the corner of the matrices.
Say that again, please. I couldn't
Maybe
hear
that
that.
if 0 is at the top left corner or top right corner. In that case, when those are the corner cases. We'll have to check whether we are within the boundary or going.
Oh, I see. So okay.
it.
So here is the thing. We can assume that everything outside is land. Okay. So you are saying that if it is a so in this case, this is pond, right? This is also pond, even though it is boundary. Okay.
Okay.
So what we are assuming is that outside of this boundary is basically this one is all land, right? Okay.
Yeah.
So this is a simple probably DFS problem, right? Or graph problem where we find the connected graphs or whatever we want to implement, right? Basically, there are a couple of approaches where we start from, say, from this first row and then go through each basically row. Wherever we find 0, we try to do DFS or BFS. Both is fine. I heard both, and basically we explore till. So in this case, we go 1 and then we found the 0. We try doing exploration, any BFS, DFS, and keep going, till I find 0 in all directions, right? Yeah. And this whole, whatever all the 0 I find, I say that this is my one pond, and then I keep doing that. And I think since we are doing either BFS or DFS, we have to basically track whether I have visited that or not, right? So that we don't go in loop.
Yeah, correct.
Okay. All right. Any question about this?
Yeah.
Okay. So, okay. Now I'm just changing the question a little bit. Okay. The question is kind of similar, but the difference is that I have given all land, and then what I was told is that, okay, mark a point with the water. So in this example, let's say 0, 0, make it water, right? So I'm going to make it water. And then tell me the island. How many islands I have, right? So in this case, how many islands I have? One. Now, if I make this 0,
2,
it will be 2, right?
yeah.
Right? If I make this 0, it is still 2.
Till 2. Yeah.
2, yeah.
Right? And if I make this 0, how many
One.
we have?
So Bhavesh, are you counting island or ponds?
Sorry,
Pond, I
ponds.
think, yeah.
Yes, I mixed myself.
Okay.
Yes. Okay, ponds. So now, if I make this 0, now it will become
1.
1.
right.
Mm.
So the question is, every time you are asked to add, make a particular point 0, we have to, at that time, we have to count number of ponds, right?
Yeah.
So maybe we can do the same approach what we did, right? Just now, what we discussed.
Yeah.
But that is a problem, right? Every time I have to explore whole maze again and again, right?
Yeah.
And this is the kind of problem where we can use some other specialized data structure and algorithm to solve this problem. Okay. Okay. So does anyone have any other approach to solve this right now? Other than the one that we solved, because in that case, that is simple one. Every time you put water, basically you count all pond, in the whole area.
So here we are going like horizontally and vertically to find the pond, but not diagonally. So when we had three circles, then we said it's a 2 pond, right? That means we were not considering diagonally to be a connected pond.
That's correct. We are just
okay.
Yeah. I mean, the similar problem. It can be all 8 direction also.
Yeah,
just for
yeah.
simplicity of discussion, I'm
Okay,
making it 4
okay.
direction.
So we can check, for the neighbor. If any neighbor is 0, then we know the number of ponds still the same. But if all of the neighbor are 1, then we can add 1 to the pond.
Okay. So what we are saying is that
in that case, if you're going to join 2 islands, then we're going to use that, right?
Yeah. So, for example, how many island I have right now, or pond, let's say?
4.
4, yeah.
4. And if I add it here, how many it will be?
1. Yeah.
1.
Right. So now let's see whatever algorithm you told, how we can apply that.
At each point, we can check in all the directions whether 0 is there or not. If that is 0, then that will merge into 1. Else, if it's 1, then we can say that this. I mean, if that particular 0 is surrounded by all the 3 sides by 1, then we can consider that as 1 point.
Yeah, and mark it as visited.
Yeah, visited, huh? Yeah, you have to take care of that.
Yeah.
So basically, what we're saying is that we just explore from the point where we are in all directions.
Exactly. Yeah.
Right. And how many times we decrease this depends on what. For example, in this example, right? Now, if I put here 0, I find in 4 directions 4 zeros. So I reduce 4 to 1, right?
Yeah. Yeah.
Now, yes. What if I have this? That means I have
2.
2 points.
2.
No.
Now, what would be the logic where I reduce 2 to 1? Because still I find in all 4 directions.
You're gonna
And the goal-
union 2 groups to kind of make it one. Make the
Yeah. What's the yes? Can you please explain your approach?
yeah. I was thinking like the in the middle, the one that was there. If we just turn it into a pawn, it could have been one group. That's what you were asking.
No, I'm saying that. So the one thing we discussed just now, right? One approach is that basically, if I'm making this middle one from 1 to 0, I can go in all direction, right? In all 4 direction. And how many 0 I found? Basically, we can merge them all. But the question is, how do you know how to reduce? How much to reduce pawn? Because it depends on how many pawns we had begin with and whether they are interconnected or not, right?
Yeah.
Right? I mean, if I have 0, 1, 0, and okay, I think I made a mistake. Okay, 0, 1, 0, 0, 1, 0, 0, 1, 0. So in this case, I have 2, right? And I make this 0, then it becomes from 2 to 1, right?
Yeah.
And in this case, I have only 1.
Yeah.
And now I make it 0 here, it remains 1, right? So basically,
so along with zeros, I think we need to have the pond ID somewhere maintained.
Exactly, right? And so that, yes, that's a very good point. So let's see that. So the things what is just told is instead of this as a pawn, right? Let's say this is a pawn, B pawn, C pawn, and D pawn, right? Now, when I'm making this 0, let's say this is E, okay? And then I'm connecting basically to 4 different pawns, right?
Yeah.
So basically, what happens is that, yes, go ahead.
But then, if let's say the A island is big, then you have to traverse, all the A island to mark it. Now become, a new. All of them gonna have a new ID.
Yes, correct. You are saying this, right? Now, and it can be big. All the island can be big, right? Right, this way. So that's a good point. So if I'm going to make this E, right? Basically, that means now I have to, go everywhere in all direction and basically change all B to E, right? Basically all, I have to change lot of places, right? Is that your point, comment?
Yes.
Yeah, yes, that's true. So that's the problem we basically try to solve with in and find, okay? It's just background how we can solve that. All right. So there are some other problem also. Interesting is, let's see if I can open this. Okay. This problem is called redundant connection, where we are given connection basically 1 to 2. So 1 to 2, 1 to 3, 2 to 3. And we have to find out that 1 to 2 and 1 to 3 already make all, vertices connected. 2 to 3 is redundant basically. Whether I have 2 to 3 or not, it doesn't matter. Without that, all are connected. Similar problem, the example 2, where 1, 2, 2, 3. So all different vertices is given. All different edges are given, and then we have to find out what are the redundant edges. In this case, the redundant edge could be any, right? 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Any can be redundant edge.
So it's kind of like breaking the cycle here.
Yes, that's correct. Breaking the cycle.
But is that one direction or both direction? Seem like the arrow show like one direction only. So we break. Let me see. Yeah. We break like 2, between 2 and 3. Then one wouldn't go. One unable to go to 4, right?
Yeah. So I did not say it correctly. The problem is it says that a rooted tree is a directed. So basically, we are going to make it a kind of tree structure out of graph. Okay. So there is exactly one node at the root for which all other nodes are basically descendant. That is what we are trying to figure out. So in this case, so tree is also a graph, right?
Yeah.
Except there is no cycle, right?
Yeah.
Yep.
So for example, in this case, let's say that this is tree, is that correct?
Yeah.
And because we know tree as a parent child, I can make this direction, right? We always have a parent have a child node, right? Now when this become graph, when I have either this or I have either this, right? Or I have either this. Any of this 3 lines that I draw, that make it graph, correct?
Yeah.
And this is what we want to find out, that whether the given all the edges, which are all the edges that we can remove, so that the structure that we get is kind of a rooted tree. Okay.
Yeah.
All right. So having said that, let's start with now. Just give me a second. Yeah, let's start with what is union find. Okay, so union find, known as a disjoint set also, and also known as dynamic connectivity, is a kind of data structure that help us to solve this kind of problem, dynamic connectivity problem. Why I'm saying dynamic is basically your connectivity change with any operation that you are doing, right? In this example of adding water and count pond, basically every time we make any point water, the whole dynamics of the structure change, right? And either all become connected, or only few of them still stay connected, right?
Yeah.
So
To visualize it, I just came up with an idea, like with a pond. Visualize as it's raining, and then it kind of like they get connected at some point. Like,
oh yeah,
instead of
good
two
point,
ponds,
yeah.
it's raining, and then yeah, I just wanted to add that.
Yeah, perfect idea. Yes. So so I'm just drawing few nodes. Okay. And I'm making few connected, right? So dynamic connectivity problem or union find help us to basically do two things. It can let me connect two components. For example, if I, let's say, if I don't have this, right? So it let me connect. It says that I can ask this data structure saying that connect 3 and 4, and then to make this connection. I can ask this data structure saying that connect 8 and 9, and it makes that connection, right? I can ask it to connect 1 and 6, that is already connected. I mean, without I putting this line, right? When I ask to connect 2 and 7, it lets me connect. And at any point of the time, I can ask saying that is there a path connecting the two dots? So I can anytime ask, is there a connection between 0 and 3, or is there a connection between 5 and 3? With this connection, if I ask saying that are 0 and 7 connected, what is the answer I'm gonna get?
Yes, I think.
Yes.
Yes. And 8 and 9, yes.
Yeah.
Right, but 8 and 0, no, right? Now,
So
to give this answer,
one quick question, Bhavesh. Would it allow 1 to 6 to get connected?
yes. I mean, I just
Because
draw it, but
okay.
They were already connected, right?
Yep. Okay.
Yeah. So this is just I'm explaining theory, but when we implement it, probably it doesn't matter if we make this line or not.
Okay, got it.
Because they were already connected. Okay. So in Clark's dynamic connectivity or union find, let us do two operations. Basically connect and basically it answer if they are connected or not. This is the only operation that this data structure can help you to do. And if we modify it a little bit, it probably can give you the kind of how many connected components I have in my system. So at this point, if I ask union find saying that get me total get count, right? It can return me 2, saying that I have a 2 connected component. Okay. All right. So far with me.
Yeah.
Yeah.
Yep.
Okay. So. Okay. So basically, as we told, right? It asks it we so union find, in the union find data structure, basically okay, another quick things. Okay. So to represent this, right? This is kind of I mean, I'm just trying to explain the name, right? Disjoint set, union find dynamic connectivity. So basically, this in mathematics or in a computer science, it is represented as 2 sets, right? One set contains 0, 1, 2, 5, 6, 7, and another set contains 3, 4, 8, 9, right? And that's why they are called disjoint set. So basically, this data structure have multiple sets. They are not connected, right? And the whole things are represented as a one data structure, right? So so we are going to basically implement the union find data structure. So let's see that what are all the APIs we need. If I have a union find class, One we already talked about it, right? Connected, right? It takes, let's say, 2, right? And it answers us whether they are connected or not. And another one is, let's call it union. So when I say union, it basically connect ing, and connected will answer if the ing are connected or not, right? So in the above example, if I say that connect 2 and 3, right, then the whole both set become one set, right? This become our whole data structure, right? It become basically one set of all the element. Okay. So there are a lot of different way to achieve this, and we'll go through it, go through few of them. Okay. So there are different terms. So first one we are gonna use it is quick find. Okay. By the way, we did not answer one question. Okay. Let me go above. How connected, when we are saying that is 0 and 7 connected or not, right? In this case, how it is going to answer us? So basically, we are going to ask, right? If 0 and 7 belongs to the same
set.
Yeah, same set or not, exactly. And for that, we need another implementation called, find their ID or whatever. We are just calling it find, okay? Find of integer I is gonna, this gives us return bool, this is return void, and this is gonna give us what is the identifier of that set. Okay.
What is the input int stand for here? Find.
In find, basically, okay. So when I say that whether okay, in this case, right? Okay. When I say that is 6 and 3 are connected or not, right? So for me to answer whether 6 and 3 are connected is basically, I'm gonna see what is, so for example, I'm gonna give this ID, right? This is A and this is B, right? Two component. I mean, it can, it is actually 1 and 2, but it will get confused between the nodes 1 and 2. But let me say that it is 1, this is 2, right? This is my first connected component, this is my second connected component, or first set and second set. Now, to answer whether 7 and 3 are connected or not, to answer that, what I'm going to do is that I'm going to say that find 7, right? And that is going to return me 1. And I'm going to, ask find 3. And that is going to give me 2. So this in find, the input 7 is basically, you are going to ask what is the identifier or which set it belongs to, 7.
Okay. Yeah, got it.
Okay. Right. Any questions so far?
Can you quickly tell me about the union? I missed the union. What does the union function do?
Okay. So now in this case, okay. So connected, we know, right? You understand connected?
Yeah. So it will say yes or no, right? Connect.
Yes. Yes. 2 and 3. Yes. Right. And then it is internally fine to do that, right?
Yeah.
Now, so the union, when I say that union 2 and 3, let's say, right? what it's gonna do is that it is gonna connect this and make all set together. After I do union 2 and 3, if I say that find 7, now once I do the union, either all become 1 or all become 2. Okay. Now if I say find 7, it is gonna return me 1. Find 3, gonna return me again 1. So basically it connects the two sets and make it one set.
Oh, okay. So it has to be always two different sets, or can I also say union 0 and 1? So they are already connected.
You can say, but there's no effect.
Yeah, there is no effect,
right?
Yeah.
Yes. So it doesn't change. So basically, this doesn't change your subsequent call to either connected or how many component you have or things like that. So you can always say that connect 0 and 1. I mean union 0 and 1, or let's say union 5 and 2 in this example. But it won't change your answer to, find union connected or total count. That is another one that we haven't written. How many basically total how many component we have, right?
Yeah.
So, okay.
But then you found 2 and 3 to be the specific points which can connect the two sets. So I guess the next will be like how to find those 2 points, right?
Yeah. Yes. Okay. All right. So there are different algorithms to do that. We'll start with the very naive one, basic one, and then we move to the optimized one. Okay. And normally when we use this data structure saying the quick find, we are going to always use the optimized one in any of our conversation. But we will go through all so that we understand how we arrive to the optimized one. So the one is the first is called quick find, right? So basically, let's say that we have a basically 10 component, right? Again, I'm gonna draw 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Okay. So I'm going to maintain my data structure using array internally. Let's call it ID. Okay. ID have basically 10 element, right? Okay. So now we are going to give them unique ID, right? Everyone. So we have to decide which one get what ID, right? So let's say that this one gets 0, right? This one get 1, this one get 3. It can be anything, right? But we have to basically make sure that all are all ID are same. 4, 5, 6, 7, 8, 9. So 0, 5, and 6 are connected. So all of their ID are 0. 1, 2, and 7 are connected. So all of their IDs are 1. And 3, 4, 8, and 9 is connected. So all their ID are 3. Okay. So this is how I'm going to maintain my data structure, right? And then I can answer all my questions, right? If I say that find of integer 1, right? Yes, find 1. Find 1 gonna give me 1. Find 7 will give, find 6 will give me, can anyone tell me? 0, right? And then and then I'm going to answer question like connected. So connected 0 and 1.
Compare those two numbers, right? So if 0 and 1 equals, then return true, otherwise.
Yeah. Connected of integer I and j, right? Basically, it is simply return find I equal to find j. Correct?
Yeah.
Yeah, correct.
Okay.
Yep.
So see, in this case, what we are doing is that we are basically changing all, and this is exactly the problem that we discussed when we are doing the pond problem also, right? Suppose I want to connect 5 and 2. That means I either go the whole array, wherever there is 0, I replace with 1, right? Or vice versa, whatever my implementation is. But I have to change all the structure, right? So union operation is not efficient in this case, correct? So let's write quick code for this. Okay, so so we are saying that this is quick find, right? Quick find, union find. So this is the class name I'm given, and it has a private int array, right? That's we call ID. And then the constructor will always take integer, and that's how many numbers of component this data structure is going to have. And so we initialize with the so initially what I'm gonna do is that each ID is basically itself. Okay, and when we run through this code, we'll quickly talk about why it is and what it is gonna do. And find we already talk, right? It is very simple. Find is gonna be
One question. So when we do this, is this array needs to be in the sorted order?
No.
Okay.
Okay. So we'll go through example also. Okay. So okay, and then union. Right, and we said that, right, when we basically connect two, we go through the whole array and replace one with another, right? So we can decide anything. We can replace ID of everything where the PID, where it is PID, we replace with the QID. So it's a for loop. So I'm gonna check, right? If ID of I is equal to PID, then I'm gonna replace that with the QID. And this is all. We already connected, right? I'm just, for completeness, I'm gonna write here.
In the above for loop, what is I is less than M or N? Like, is the length of the nodes, like length of
length of ID, I think.
Oh, so okay, yes. So what is N, right? That's the catch. It's the size of the. So we haven't maintained that. Very good. So this is the size of array basically, whatever N we got here.
Yeah. Okay.
Okay. So size. Okay. Integer size, right? And that can be, we can initialize that to N. So this is like how many components we have. Okay. Or we can basically easily find out by integer size also. Actually, I don't need to maintain that. Sorry. I'm gonna, since we are using all this language, right? Not just C++. I can find by ID size, right? So I'm gonna change my code.
Yeah. Array dot size.
Yeah, array dot size. That's correct. ID dot size. Okay. Return if find P equal to find Q. Okay. So this is very simple code, right? What we are doing is basically given so this is initially we are saying that I have a 10 Union Find data structure with the 10 component. So when we initialize this, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And my count is equal to 10. Basically, I have a 10 component. And all are separate component, right? Count of component is 10. This is my ID array. Now, could you please help me to, connect few of the component? Just tell me which one to connect and we will change accordingly.
0
and anyone have 0 and
5.
0 and 5. Okay. So I'm connecting 0 and 5, right? And based on our code, right? What we are doing is that we are finding so we are basically connect 0 and 5, right? So PID of 0 is what it is?
0.
4, 5, 6, 7, 8, 9. PID of 0 is 0 and PID of 5 is
5.
5, right?
5.
And basically we are going through whole list, right? And wherever I am seeing 0, I'm replacing it with 5. Okay. So this become now 5. Okay. Help me with some more, please. Let's say connect 0 and 1. Okay. I'll do 1 and 2 also. Okay. So this become again 5. 1 and 2 again become 5, right? Okay. Let's say 7 and 8. So 7 and 8. So then 8's parent ID or ID becomes 7, right? And 3 and 8. So there is 3, that become whatever is 8. So that becomes 7.
Are we running our algorithm?
Are we running?
Are we running our algorithm right now?
Yes. Yes. When we are saying that connect, we are basically going through this union code where we find the ID of first, ID of second, and replace everywhere that we find PID, replace with the QID. It's a for loop on
I have a question here. So when you connected
Yes.
8 to 3, you took the 7 as the ID. But what if suppose we had taken the 3's ID and changed the 8 ID to 3?
It doesn't matter, I think.
Oh,
it doesn't matter, but basically we have written the code that way. So I'm just sticking with this code,
so
but
we are
it
going
doesn't
through
matter.
the whole array anyways, right? So
yes, we are going to the whole array, so it is not going to change anything.
Yeah, okay.
Yeah, okay. So any doubt about this?
So can we, Bhavesh, just a quick question. Can we say that all the nodes are distinct here, or they can be same? Like, can 5 repeat somewhere?
Okay, when you say all
like
the nodes
0,
means
5, 1, 2, right? So we started 5 as a parent
Yeah.
node and then assigned it to 0, 1, 2, right? Or suppose after
Yes.
4, 9 we had 5 again. Can there be a scenario like that, or
after 4,
like we have
9.
another node with?
Oh, I see. No. All okay. A very good point. So all node are distinct nodes.
Okay.
When we say that I want a union find of size 10, that means it is 0 to 9. It's kind of we can call it as an index. So no?
Got it.
All are distinct. Okay.
Yeah. Thanks.
Okay. Any question about this? It is very simple algorithm, right? Okay. So let's find the runtime of this, right? So in initialize, so in constructor we do something right here. What is the runtime of constructor?
Open.
Yeah. What is the runtime of find?
Constant.
O of
1.
One. What is the runtime of union?
N.
N, right? And what is the runtime of connected?
1 only.
Right. So that's why we are calling it quick find, because see, our find is 1, union is not 1, right?
Yeah.
Okay. So now let's quickly walk to the other algorithm. Okay, where okay, so just the time check. Do we discuss normally more than 1 hour or 1.5 hour or less? I don't know about this session.
2 hours. 2 hours, I think. Last 2.
Okay.
2 hours. 2 to 1.5.
So everybody, okay, that's fine. We definitely have that much thing to cover. Okay, so this is quick find. Anyone have any question about it? Otherwise, we're quickly gonna jump to the little bit more complex implementation of it. Okay.
Yeah.
Good. So the next one is, we are gonna call it quick union. Right. So in previous one, we saw that my find was O of 1, but the union is O of n, right? And so we have basically changed something so that, my union is a little bit optimized. Find might not be optimized, and we'll see how to make it optimized later. Okay. So what we were basically storing till now, right? 0 to 9 again. So this will be my initial thing, right? Now, let's say that 0. Right, those are all the node. Now, instead of we are maintaining one node, right? We are gonna do little bit things differently, right? What I'm gonna do is that I am gonna say that connect 2 to 9. Okay, union 2 and 9. Okay, and the way I'm gonna do it is basically I'm kind of changing. I'm not going to find the whole array, okay, and say that. So in previous one, right? What we do is that when we say that connect 2 to 9, I'm gonna say that pi basically p2 is equal to 2 and p9 is equal to 9, and then basically go through whole array, and wherever there is 2, replace with the 9, right? And that's why we got O of n. In this case, I'm simply gonna do saying that, you know, when I say that connect 2 to 9, I'm gonna change either way, you know. Let's say that change the ID of ID of the first with the ID of second. Okay, so in this case, I'm gonna say that I'm gonna just simply do this. Okay, any so our representation kind of change, right? Did you notice that? So see, zeros parent, if we call it as a parent or whatever, right? 0 is 0, 1 is 1, 2 become 9, right? And everything is same. Okay. Now I'm gonna say that now connect 9 to 4. Okay. Or let's say that connect 4 to 9. So what I'm going to do simply, my connect would, or union, right? It is connect. I'm just mixing. Sorry about that. Okay, union 4 and 9. So my union is very simple now. What I do is that P of 4 replace with P of 9. So this become 9. Okay. 4 come here. Okay. Now I say that connect 4 to 3 or 3 to 4. Let's say that union. Union 3 to 4. So I'm going to replace whatever ID we have here. Did I do correct?
Yeah, now instead of going to 4, I think it's going to go to 9. 9 is going to be the parent. If I'm not.
No, I think I made some mistake. Okay. Yeah, okay, that's fine. Yes. Yeah. So yeah. So we are finding the parents of yes. So 3 days, right?
Yeah.
And this become 9. Okay. Now, but you know, these things can be, you know, become a little bit problematic, and we'll see that, right? Now, what I'll say that union 5 or other way 9 5, connect 9 and 5, right? So in this case, what happen is that now 5 come here, right? And we are replacing 9 with 5. Okay, so far with me? No. Any question about what we are doing, how we are doing?
So we have kind of sort of messed up with the original, I mean the previous group or union, isn't it? I mean with this new link.
Say that we are kind of.
So this time we replaced the union ID of 9 with 5. So now 9 is kind of taken out of group 9. So that formed a new maybe union of 5. So there are two now unions with ID 9 and with ID 5. 9 was earlier part of 9, but now it is part of 5.
So now the ID is not represent the group ID actually in this case. Let's understand it, right? So previously we were saying that ID is a group ID, but now in this case, ID is not actually group ID. We have to maintain group, how many count of group is separately. Okay. But what I think is that previously in union, basically we are going through the whole array, right? In this case, we are simply, when I say that union 9 and 5, what I'm saying is that find the parent or PID, right? Not PID, but what I call it is find the P of 9 equal from ID array, right? Is ID of 9, right? And P of 5 is equal to ID of 5, right? And then I'm saying that actually I don't need to find this also, but we'll need it later. My union code is very simple actually. It is just say that replace ID of 9. Oh, sorry, it's not that.
So it's kind of, in other words, like we're improving the time complexity of the union instead of the find, correct?
That's correct. Find 5. And then I'm saying that ID of say 9 equal to P of 5. Right? My union code is simple now. Right? Now, but what would be my find code? When I say that find parent of 2, right? ID of 2, what is that code? How does it look like?
You have to find the parent, so you gotta kind of get the parent of a parent and until we get.
Exactly, right? So if I say that find of 0, simply 0, right? Find of 1 is 1. Find of 2. So at the 2, we have stored 9. So basically that is not the answer. So answer is when both match, right? When the index and value match, that is your answer. Right? So in this case, 2 and 9, so that doesn't match. So basically from here we go to the 9. And 9 also doesn't match because 9 stores 5. So from here we go to 5 and 5 and 5 match. So then when I ask find of 2, basically I return 5.
So the complexity is gonna be the height of this tree.
Correct. Yeah. Complexity is gonna be height of this tree. And now we can say that still now find is returning your ID, right? So there's no direct relationship, but basically when we gonna ask find 2, 4, 3, 9, and 5, all is going to return me always 5.
In the union, right? There's two parameters, and the first parameter always smaller than the second one. So can we do the same? Like the last one, we would say, okay, the smaller parameter will go first, and then the second parameter. So that means that will be union 5 and 9. So if we union 5 and 9, then 5 will be the child of 9, right? Because I'm talking about the order of the parameter.
Yeah. So you can do anyway, right? Basically, when you say that union I and J, right? So either you can make I as a child of J or J as a child of I.
Yeah, but if we follow the order, let's say the first one, we always smaller than the second one. So would that like reduce the height of the tree.
So see, okay, yes, that's a good point. Probably we will go there. So what you're saying is that, but how you know that, right? What is the size of the tree?
No, you compare, like you say, the index, the ID always the index of the array. So in this case, we pass in the union, first parameter.
You are saying that union 9 and 5, then we should make 5 as a child of 9?
We will make it become union of 5 and comma 9.
Yes and no, right? What if I have not 10, but let's say that 11? Okay. So what I'm saying is that I have a 11, right?
Okay.
I mean, I don't have 10 element, but 11 element. This is 10, right? Okay. Now I say that union of 5 and 10, or 10 and 5. Which one will you make child of what?
5 will become child of 9.
Yeah. So that is going to get us same problem, right?
Right.
So basically, this index doesn't represent how big it is. You can't say that. It is always depending on what kind of connect query. Basically, we union. This 4 become this tree structure. If that union come in different order, we might have different structure here.
But there's also, I mean, I saw examples for union find. There was depending on the weight of this union.
Yes, we are gonna go there.
Oh, okay. So this is when it comes to the order of the relationship, right?
Okay. Yeah. So we improved a little bit, right? Whatever we were doing previously. So what things we improved here? We improved our union. That is a little bit faster. But then find, we did not do good thing in find, right? Because find we have to go through parent, right?
Yeah.
And that might be bad thing. Let's quickly write the code, but let's see. So everything is going to be same, right? So our constructor is same. Only thing changes find and union functions. I'm just gonna write that. So find, when it asks for find, right? What we say is that while I is not equal to ID of I, right? I'll say that I is equal to ID of I, and then return I. Right? So this code is very simple, right? Basically, what we are maintaining till now is that when the index match, that is your root node, right? So when we want to say that find 2, basically 2's index, whatever the value we store is 2 is 9, so that doesn't match. That means we have to go further. Then so we go, our ID become now 9. Find 2 become find 9. Find 9. It is say that 9's parent is 5, and that 9 and 5 doesn't match. So my I become 5, and I'm gonna do find 5, right? And now let's say that find 5 and 5 match. So we basically run our while loop till the both match, where till I become the ID of I, and then we return the I. Okay. Any question for this? Okay. So, and our union we just wrote, right? Our union is simple.
So finds time complexity will be like in worst case O of n.
That's correct. So we kind of did not improve anything. In fact, we made a little bit worse, right?
Yeah.
Okay. Okay. Not a problem.
And Bhavesh, I think there was one more function you wrote earlier, count.
Count,
so,
yes.
So that would remain O of n in both the cases, right? Because we have to scan the whole.
So, yes, basically we haven't done the count code here, but what happened is that whenever, so count initially start with all the element, right? Whenever we do union, right? And whenever we change it, whenever we do this, right? Just let me write in this example and it will be same. So when we do the find of both, right? P and Q, what we do is that if I is equal to J, we simply return. We don't do anything, okay? Because both belongs to same group, right? Otherwise, we say that ID of I is equal to ID of J. If they both are not same, that means they belongs to the different group and we are connecting it, right? And at that time, I'm gonna reduce count that I maintain globally. If we haven't, right, we can write that here in my constructor, right? So I have private integer, right? I actually have a private integer count also. And that count is basically initialized with how many elements we have in the beginning. Okay. So this is how basically we maintain count. If we connect, we reduce it. Otherwise, we don't do anything.
So potentially for the count, we could have like two group, right? And later we join two group to become one group. Then wouldn't that the count had to be decreased more?
Yes,
because now we join two group to become one. But this case count only decrement by one.
Yes. So let's see.
That won't make the maybe a quick comment, Bhavesh, that won't make any difference because when you were building those two separate groups, count was actually decreased in those events. So
yeah, it only decreases whenever you are assigning one element to a group.
Another.
Yeah. Okay.
Yeah. So yes, both comments are correct. Basically, this count is keep decrementing. When you say that you have only two groups, that means you already have reduced count so much to make two groups, right? Because every union basically reduce the count if it is going to make a new connection.
Okay, it's a kind of aggregate count.
Yeah.
So you're saying quick union is not that quick because we're using the find, right?
Yeah.
That's what you said before.
Yeah. So see, in a quick find we had a constructor is same n, but find was 1, right? And union was n. But now we end up basically converting find also to n, right?
Yeah.
And union become union, although we are calling it quick union. You know, we think that it is quick, but you know, we may end up finding when we are looking for the parents, we end up going through the whole array, right? The whole tree.
Maybe it will give benefit when nodes are all connected.
It will be benefit when nodes are all connected, but you know, so I can always have a structure that is very weird, right? Like this. Let's say I can end up having a tree that is like 1, 2, 3, 4, 5, right? Can I end up like this tree?
Yeah.
Now, if I have to do find, it is gonna track O of n time. Is that correct?
Right.
Right. So if both belongs to different component, it is little bit faster. But at the end, when everything is connected or both become, you know, two big tree, it's depend on the tree structure, how your tree structure is. I mean, the invisible tree, how it is building, right? And based on that, basically, it can be efficient, it cannot be efficient. But worst case, we have to tell that it is O of n, right?
Yeah.
Okay.
Yeah.
And
But at
And
most,
by any way, can we just make the node point to the parents, something like that?
yeah. So that will give you some improvement, and so we are gonna do 2 improvements to this our class, okay, and that will give you the most optimized solution, okay. So but so far we are clear what we have done, right? Any question?
No question.
Okay. So so what we need is a quick find and quick union, right? So now when we do quick union, our tree is becoming skewed, right? In a sense, suppose I have a smaller tree, right, and I have a larger tree, right, and I am connecting these two, right? Let's call it, this is P and this is Q, right? I am connecting P and Q. So there is 2 ways to connect P and Q, right? Either Q is one tree, and then P become child of that tree, right? Or other way is P become parent T, that is small tree, and then Q become child of it, right?
Yes.
Yeah.
So which one is more efficient?
The first one, because
First,
we're not increasing the depth of the tree.
exactly. So basically, if I somehow maintain how big is my tree, right? And when I do the union, right? When I do union, if I basically blindly saying that I connect P to Q, even though I'm connecting both P and Q, but which ID to make child of what, basically, if I take the decision based on some other variable that I maintain, right? Other memory that I maintain about the size, that would be really helpful to me, right?
Yeah.
So
Yep.
we are gonna augment our data structure, whatever we have written so far, okay, and exactly implement that, right? So we have a quick. By the way, the third one that we are discussing, it is called weighted quick union. Basically, based on the weight, I'm gonna make child of one another, right? So let me put that name here so that we remember. Weighted. So I'm gonna do again quick union only, and based on the weight, I'm gonna do quick union, right? So here I'm maintaining count, then integer ID, right? Now I'm gonna maintain integer size also. Okay, simple. And initially, basically, we run the for loop, right? For int I equal to 0, I less than n, I plus plus in a constructor, right? Basically, both are going to be initialized with new int array of size n, right? Same. And when I do this, we do this idea of I equal to I, right? And initially, I'm going to make size of I equal to 1. So all size is 1, okay? So, and when I now do the union, right? So we are going to find P, right? And we are going to find Q. And if now simply becoming I to J or J to I, right, child, what I'm going to do is that I'm going to check size of I. If size of I is less than size of J, is that the name we are given? Okay, SZ, right? That means my, the which tree is bigger? Q is bigger, right? So J is bigger. So then what I'm going to do is that I am going to change the I to the J. Okay. And also I am going to change the size of I equal to size of I plus size of J. Okay. And otherwise, in else, right? If this is not the case, that means J is bigger than I. So in that case, I am gonna do the other thing. ID of J equal to I, and then size of J plus equal to size of I. Okay. Is this code clear? We can walk through some example.
Yes, it's clear.
Okay. So now, so what basically when we are connecting to, right? So in this, our example here, right here, when we were connecting 5 to 9, right? Now, instead of 9 become child to 5, 5 become child to 9, right? And basically we maintain the weight also. Okay. Do we want to run through this example?
I think that would be helpful, Bhavesh, because I have a question there in the first block.
Okay.
So I was thinking that maybe size of J should be increased in the first block because J is the root. But
say that again.
If you scroll up a little bit.
Yeah.
So here we are comparing in the if block that so in first if block basically J is bigger, right? So we are making J as the root.
Yes.
So should we not increase the size of J instead of I?
Yes, that's a good point, and that's the code word. Yeah. So your doubt was right. So this become. Thank you for pointing that out. Okay. So basically, since we are making J parents, J's size is going to increase, right? Okay. Now remember that in this case of size is our size of the whole tree. That means how many elements in that tree. Okay. It's not the height actually, but it is going to help us.
So I'm sorry, Bosh. Can I just the size of and the second size when you're setting it I plus equal to it should be J, right? Size of J at the end. I mean.
Yes, it is. Yes.
Oh, okay.
I didn't do all correction. That's correct.
Okay.
Yeah. Okay. All right. We can just to quickly understand. We can run through some example. Okay. again, we are going to have two array right now, because it is, this is ID and this is size. And as we told, size is always 1 in the beginning, and this is, oh, no. Okay, help me with again connection, please, so we can run our algorithm on that. Which one we should connect?
1 and 7.
1 and 7, right? You said 1 and 7?
Yeah, 1 and 7.
Okay, so 1 and 7 size both are same, right? So
it will go to else block.
It will go to else block. So basically we are making ID of j to ID of I. So we are making ID of j, that is 7, to ID of 1, right? Is that correct?
Yeah, correct.
Oh wait, it is. So this become 1, right? And size we are changing here, right? This size become
2.
2. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 5, okay, 6. This is 7, 8, 9. Okay. And we connected basically 7 as a child of 1. So I'm just going to rewrite here 6 and 7, right? Okay. Some more?
4 and 8.
4 and 8. Okay. So again, it is same as 1 and 7, where if you are taking that 4 and 8, then basically 8 becomes child of, right? Child of 4. This is our 9. Okay. Here, this will become 4, and we are changing the size of 0, 1, 2, 3, 4, and it become 2, right?
Yeah.
Okay. Let's quickly run through example where we basically making smaller as a larger child.
1 and 2.
1 and 2. Okay. So 1 and 2, now we are gonna go into the if block, right?
Yeah, correct. If block.
Basically, where we are saying that size of I is less than size of j, or 1 and 2 size. No, we are still gonna go to else block. But when I'm connecting 1 and 2, size of I is equal to 2. Oh, yes, it is not less. So we are gonna go again this block, where we are making 2 as a child of 1, right?
Yeah, correct.
So we are still, so
size of 1 becomes 3.
Size of 1 become 3, that's correct. 3. And index of 2's become 1, right? Okay.
And
now
next we can go for 9 1. 9 and 1.
9 and 1, right? Okay. So yes. So in that case, 9 size is less than 1 size, right? So we are gonna go into the first block. 9 size is less than 1 size. So instead of making now if we have a not the weighted algorithm, we could have made a 9. 1 is a child of 9, right? But in this case, basically, since we are doing that, we are gonna have 9 as a child of 1, and then size of 1 is become 4, and 9 index would be
1,
right? Okay. Now, still the tree can be bigger, right? That is possible, right? Can tree?
Yeah.
Right. I mean, it can be it can become bigger, but basically, so here one interesting property we are doing, right? If both sizes are same, then what we are doing is that we are basically, it doesn't matter which becomes which child, right? If both sizes are same. So how we can say that we are now maintaining the balanced kind of tree? In a sense, it's not balanced, but the tree structure is like that, so that we can say that finding the depth, right? My depth of the tree is log n. Right? Because this is helping only if I am saying that my depth of the tree is giving me the property of log n, right? Basically, when I'm going to find the parents, in this case, what I'm going to improve is finding the basically find function, so that I don't have to go through the whole scoop tree where my complexity become O(n).
In the worst
Right?
case, what the tree would look like if we do the rank?
Yeah, that is what. What is that?
Yeah,
rank?
we do with the rank. In the worst case, what the tree would look like.
Can you please tell me a little bit more?
Okay,
so you are saying that if we do rank,
yeah, we do with rank, and then we keep joining the one with higher rank, right? And then I try to visualize, in the worst case, what the tree would look like.
For weighted tree, like in this graph, weighted algorithm, how the worst case tree will look like.
Okay, so worst case tree would look like something like this. Okay, so let's say that I'm just drawing another one. Okay, 1 has a child 2 and 3, right? And 4 has a child 5 and 6, right? Okay, and we connect 1 and 4. So worst case, it will be 1, 2, 3, and then 4, 5, 6. So basically, we say that height difference would be no more than 1.
Okay.
Okay. And let's quickly discuss about it. We were not going to long proof, but basically what we are saying is that if the both tree are same, right? Both tree are same size, right? In this case, both tree are same size, right? 3 and 3. Then when we merge that, we are increasing the size by 1 at most, right? Because in this case, you see that, right? Now,
yep.
and when it happens, basically, our total number here becomes 6, right?
So, Bhavesh, you said we increase the size. Do we increase the size by 1, or we increase the height by 1?
Height by 1.
Okay.
So size not by 1. That's correct. Okay, thanks for that. So here it was 3 and 3, right? Here becomes 6. And if you see that height, here it was size 1, right? Height, or 2, whatever we call it, 1 or 2, right? So either if we call it 1, then this becomes 2. If we call it 2, then it becomes 3. So we increase height by 1, but we are doubling the size of the tree. Is that correct? Because both size was equal.
Yeah. So
Yep.
is there any consequences of doubling the size, or it doesn't matter?
No, so that's where we can say that our tree maintain this property, because in any tree, right? Suppose it's a full tree, right? So when we go to next level, how many elements we have? So this is a level 1, level 2, level 3, level 4, right? How many can I have in level 1?
2 raised to power L1.
2 raised to power?
L1. L1 is 0, let's say. That's a 0th level. 2 raised to power.
Right? Okay. So yeah, and then here. So here there is a 1,
32.
here there is a 2, there is a 3, there is 4.
4.
Correct?
Yeah.
No, sorry. 2.
At
Yeah,
L3
L
it
minus
will
1.
be 4.
2 raised to
4.
power L minus 1.
Yeah. 4, then 8, right?
Yeah.
So see, what we are saying is that whenever we go from one level to another, our size become double. If it's a normality, and that is how we say that here also, when we join the two same size 3, then it increased the height at most by 1, but then it still retain whatever property we want, that our depth is always optimized for all the nodes.
So we are talking about the worst case only, right here?
Yes, worst case only. That's correct. Best case could be like,
which is
this
not
one
that
what
bad.
we have here. This is best case, where everything belongs to one parent, right?
Yeah.
Okay, so clear so far?
Yes.
Yeah.
Okay.
Yeah.
So what improvement we did now?
Find search quicker.
Right. So let's just quickly, let me write it down. So initialize is same, right? We didn't change anything. So basically there is an operation called union, find, and connected, whether he's connected or not, right? So in quick find, we had a union was n, but because find was fast, right? In quick union, we had everything kind of n. Find can be, n, not n, but depend on the tree structure, depend on the data input.
Quick union is 1, right? Quick union is 1.
Okay, so we think it was 1, but not 1. The reason is that, let me go back to the code. See, union depend on the find, right?
Yeah.
Yeah, and find can take n.
And
it
find
just
can
appears
take
to
n.
be, yeah.
Sorry, yes. Yeah, this, yeah. Find can take, in worst case, it can take n, right?
Yeah.
Yeah.
So basically this both can be okay, can be not be okay, but you can't say. In worst case, it is always n. Okay?
Yeah.
So this is weighted quick union what we did, right? Where we improve the find to log n, right?
Yeah.
Is that correct?
Log.
Yeah.
What about connected?
Connected
also log
it's
n.
log n too.
Log n based, yeah.
And this also log n?
Yeah.
Because in connected and union, we are using find. So that basically drive our complexity, right? Find basically drive most of the complexity here in union and connected both. Okay?
Yeah.
So we improved a lot, right? We started with N11. Now the weighted quick union, we basically, traded find complexity of find with the union becoming everything log n. Okay?
Yeah.
Any questions so far?
No.
Okay. So we will do the now final one, and that is basically doing all the optimization we need. Okay. So I mean, not I am calling it. Whoever is invented, who call it weighted union with path compression. They call it path compression. Okay. So weighted quick union with path compression. Now let's do this. Okay. So let me draw a little bit big tree here. Okay. Oh, I can't have a repeated number, right? Okay. Now, this is just for example.
Yeah,
I have.
2 is repeating.
I don't know how I. Huh?
2 is repeating, number 2.
Yeah.
2 is repeating 0, 1. Oh, okay. We can definitely. This is easy. Okay.
So
I'll make it 1. Okay.
yeah.
Okay. So. All right. Now let's say I want to do find of 9, right? When I do find of 9, what we'll do? We'll run a while loop, right? While F9, right? So from F9, this while loop, we'll go to what? 9's parent is 6 because its index is not same, right? If we go this way, right?
Yeah.
So basically, what we are going to do is that we want to do the find of 9, right?
Yeah.
And it should return 0. So basically, we go from 9. From there, we go to 6.
Yeah.
Right? And then we go to 3, 1, and 0, right? And then we return 9. Right? So anyway, we are going through all of this node, right? Basically, we can do one more optimization, and that is called path compression. When we do this, right, once we find that what is its parent, what we do is that any node that we touch on the path, right? For example, 9, 6, 3, and 1 we touch, right? What we're going to do is that we're going to make it a child of parents, all the node of this path, okay? So basically, at the end, what I'm going to do is that I'm going to remove this, 3 and 7, right? What we have. And its parent previously was 1. I'm going to make it 3 and 7 and make it 0 as a parent. Now 6 also, right? So I'm going to remove 6, 8, and 10. Uh-oh. So 6, 8, and 10 become here. And then 9. 9, 11, and 12. So 9, 11, and 12 comes here. Okay. So what I did is that whatever path I took to find my root, right? Basically, all of that path, I made it as a direct child of the root node. Okay.
Yeah.
Let me write the code for this.
One question here.
Yes.
So if we were using the weighted algorithm, then such kind of tree would not have been possible, right? The previous one that you.
That's correct. That's why I says that I am gonna, take that example to explain this concept. But you still can have a big tree, right?
Yeah.
So what I'm saying is that you still can have a 0, 1, 2, 3, 4, 5, 6, right? 7, 8, this kind of tree, right?
Yeah.
And in this case, suppose I'm doing the find 8. What I'm going to do is that anything that I touch in the path of 8, right? So 5, 2, and 8, right? So 2 and 5, and here 0, right? So that I'm going to make parents. So basically 8 comes from here and comes here. 5 and 7 comes here as a child and comes from here and here. Okay. Yeah. So I'm kind of making my tree kind of completely flat, if you see, with every find.
So every time you do find, you kind of clean up, right? Like
yes,
sort
exactly.
of.
Sort of. So although we have a log n, I'm reducing it even further now.
Below log n.
Below log n, yes. Okay.
What will?
But this will be n log n, right? Because we are touching all the points again, and we are recurring.
See, we have to touch all the point anyway in find, right? So one time I touch it. If I am doing find again on, let's say, so when I did find 5, I touch everything, right? So basically I had to go to my depth of the tree, right? Let's say in this case, suppose your depth of the tree is 10, right? Okay. So your depth of the tree is 10, then you went to 10 node, right? And once you change that 10 node, now anything in that path, you do the find again, it is going to be flat, right? So now next time I have to do find, it is not going to take log, my depth 10, because my depth is become now 1 or 0, whatever you call it. It directly connected to root, right?
True.
So a question. So this this kind of tree, it's not going to be possible if we were using the weighted union. I mean, weighted.
No, well, it's possible, right? See, we are not changing the weight. Okay, here is the thing. The root is 0. Did we change the weight of the root? Right?
No.
We did not change weight of root. Is that correct?
Yeah.
Yeah.
Only thing we did is that I made it more flat. That's it.
Yeah, but what I'm saying is, when we do a weighted quick union, we will get flat tree. Correct? Anyways.
Say that again.
I'm saying if there is an existing tree and we try to do find with path compression, that's the most appropriate application. But if we do a weighted quick union, we don't need to do compression because it's already kind of compressed. Is that true?
Well, you will be surprised to know what is the complexity of this. We'll go into that detail. I'm just going to tell you this. It's difficult to prove, but I'll tell you what is the complexity if you do the path compression. Okay.
Yeah. Last time we did on the weighted, right? And we see that it multi-level. It's not like, only 2 level, right? We do see that child and grandchild.
Yeah, exactly. So
yeah, we
weighted
see
doesn't
only.
weighted doesn't mean that the levels depth of the tree will be 1 or 2. It could mean depth of the tree can be 10 or like more.
Most is log n.
Yeah,
but can we say like the weighted quick union makes a tree slightly more balanced instead of being more cubed?
Yeah.
So, see, that's correct. Weighted quick union makes tree balance, so that your complexity of find is becoming log n, since it is balanced tree, right?
Yeah.
Yeah.
Okay. But still, it is log n.
Right.
Log n is better than n, but for some of the problems for which this data structure is used, that is also not better.
Absolutely, yeah.
Okay.
Yeah.
Okay. So we'll quickly write the code and then quickly discuss what is the complexity. Okay. So in this case, our code for the connected is same, right? We are not going to do anything, any change there. The only change we did in our find. right? So previously what we used to do is that I'm saying that root is equal to, so we had a white root, right? While loop.
Root.
ID of P, right?
Same.
Right? Root is not ID.
Yeah.
Wait. Root is not ID of root, I think, instead of P. Because I defined that, right? I'm going to change that. Then what I'm going to do is that root equal to ID of root, right? That is what we are doing.
Yeah.
And basically we are just returning root.
Root.
Right? Instead of before returning, I'm going to flat my tree. So I'm going to traverse one more time, whatever I have did till now. That's why I take root differently, because I still want to see from where the request came. Okay. New P equal to okay. And okay. So what I'm doing is that I'm finding the root, then I'm going through same path again, right? By using this P that we haven't changed. And basically, I'm flattening my tree. All the parents that I'm coming, that I'm touching, I'm just setting their parents as a root, so it directly attached to the root. Okay. So this is the only things I have to do one more time in find. Okay.
Yeah.
Okay. Now, how much it helps, right? So weighted cube union with path compression, right? And we do amortized analysis. Amortized means, as we told, right, in the beginning, this algorithm is used when you keep doing connectivity, saying that union and a cube ask question whether you are still connected or not, that kind of question, right? So for that, if we do the amortized analysis, this complexity of this, basically your tree depth will not go for any practical purpose more than 5. Okay. So I don't have understanding to explain that basically complexity, why it is derived. I can give the source, some paper that explain that. Even the book that I refer, algorithms by Robert Sigig, that also says that that is out of this book, basically the proof of that, why it is like that. Okay.
Corman, I think.
Corman, yeah. So okay, no. So the book I am referring is sorry. You are asking about book, right?
Thomas Corman, I thought. Okay.
No. Algorithms by Robert Sedgwick. Maybe this spelling might be wrong, but yes, this is the Sedgwick, Robert Sedgwick. There's a book called Algorithms. Okay. So, none of this book might have the, none of, even the CLRS, Thomas Corman doesn't have a analysis of that. but they call it a log star. Okay, so it is relationship of log versus log star. I'll just write quickly to understanding. They call it the complexity of log star. Okay, so n and log star of n relationship, right, is something like this. For n is equal to 1, log star is equal to 0, n equal to 2, log star is equal to 1. For n equal to 4, log star equal to 2. N is equal to 16, log star is equal to 3. N is equal to 64k, so 65,536 or something, right? It becomes 4. And to go to 4 to 5, it takes 2 raised to 65,536. Okay. So for all practical purpose, that's why I'm saying that we can say that its complexity is 5. Depth of the tree is no more than 5. That's why we say that it's kind of close to O of 1. Fine. With this quick union with path compression.
So is it because we won't have that much of a memory RAM to get a tree in a memory?
Say that again.
Something like
we
that.
Don't have?
Because we won't have that much memory when we are actually calling the whole tree or the whole array in a RAM actually when we are trying to do this thing. So is that because of that limitation we can't go more than 5th level?
Oh, no. We can go more than 5th level also. I'm saying that, okay. So next level would be, actually, I'm saying that for all practical purpose means none of our practical problem nowadays, at least right now we have, is bigger than this.
Oh, yeah. Okay.
This will become 2 raised to 65,536. See?
That is too much for us. Yeah.
It is 2 raised to 2 powers. Basically, every time it goes 5 to 6, that the previous one become its power. So this is too big problem to even have it right now.
Right.
Okay. If you have that problem, you can still it just go by 1 up.
Interesting.
Okay. So that's why we say that it is. So with this, practically our find is constant time. Okay. And when find become constant time, I'm just going to write it saying that it is O of 1, right? Connected is become constant time, right? And then union become constant time because that both are dependent on find and connected, right?
Right.
So this is the algorithm that we normally use whenever we use union find, and we say that this will union 2 things in constant time, and you can answer this question, is connected or not in constant time. Okay.
What is this union by rank? Because they have used for for proving that they are putting rank 0 into rank 0 bucket in order to prove this log and star.
Yeah. So you see, union by weight we did, right?
Yeah.
Union by rank means we actually maintain the height.
Okay.
And when here weighted quick union we did, if you say that you want to do union by rank, so instead of maintaining the weight, you basically maintain the height, saying that what is the height of this tree and the height of this tree. Now, that algorithm is a little bit more complex to do path compression. You imagine, right? Why?
Yeah.
Because your height is going to change
every
the
time,
moment you do path compression. So if you want to, combine path compression, then the easiest algorithm is weight, because when we do the path compression, weight is not changed for 0. But if you do, let's say, rank, your height is changing the moment we do path compression. In this case, height was 1, 2, 3. After we do that, probably become 2. So we have to recalculate it. It's difficult to maintain that when 0 can have many child.
Oh. Do we have time to go over all the problem?
We are. I'm still available. I can still discuss problem. It's up to everyone else what they feel. we should go ahead, we should discuss, we should just quickly go through this in context of quick find?
Yeah, I'm available. I want you to learn the application of it.
Or how about we do it next Sunday? Maybe a couple of problems, and in the meantime.
Yeah, can we go through all these problems next Sunday then?
Yeah, that makes sense. So one thing, Bhavesh, like, can I say, like, if I have to do a very quick thing, like, like just find the islands, can I just use quick find for that? Because I find like that wait for quick find with path compression to be more complex to implement in an interview.
Yes, you can do that. But if you see the code, I mean, maybe because you have known this first time, right? But if you see the code, we haven't written many lines, right?
Mm-hmm. Okay, so
yeah. So I completely agree with you. Basically, if I have to do, say, find island, I would assume that I already, the way I start is saying that I already have a union find with these things, saying that it give me whether it is connected or not, and I can union. Now it's up to interior to steer towards saying that, okay, show me implementation of quick find, or show me solve this problem using quick find. I think a lot of this problem will become simple once you have say that I already have existing quick find, and then interior want to go in the detail, you can talk about quick find implementation, right? For example, if you are going a problem that involve priority queue, most of the time we don't implement priority queue, right? Because priority queue itself become one interview question. We say that I have a priority queue and I'm going to use my max for min priority queue. So same way, if you want to find algorithm, find island problem, if you want to use quick union, you say that I have this data structure available, it has this function, and I'm going to use it in my code, and then we can go either discussion of quick union or this problem or both, depending on how much time we take.
It makes sense. Yep.
So let's assume that we already have the union file written. So the number of line of code we use to find the number of island when we use union file versus like depth first search, which one will be shorter?
I think both would be same. As far as I know, the reason is that in both cases, right, we have to basically go through the all whole array once. Is that correct? And if we do DFS, basically I have to maintain extra memory for visited path, visited node. And if I do quick union, still I have to maintain extra memory for this quick union data structure. So memory wise also both are same. Okay. So I don't see any problem there. But this kind of problem where we started, right? Say that we want to connect the island also, right? This one can be now solved with the same complexity, where we can merge water bodies, or we can merge ponds very easily without doing every time DFS or VFS.
Okay, so it's like more on dynamic membership verification.
Yes, exactly. See, that's correct. I think what you are saying, that is true. I think that's where we started. Yes, we call it dynamic connectivity also. I mean, wherever we need this kind of connect, basically we have to answer every time, or most of the time we have to answer whether you are connected or not. Every time you have to answer, you don't want to go through the whole structure again and see whether they are connected or not, right? You have a predefined structure that you can keep evolving, and every time when you evolve also, it is O of 1. Basically, when you connect to component also, it is O of 1. When you ask whether they both are connected or not, is also O of 1, kind of constant. Yeah.
Yeah.
Okay.
So if you have m set operations for n nodes, so it could be like m into that log n star, right? Or
if you do the m such operation with the yes, that's correct. Yes, yes, it is. It would be the m into yes. So m is basically you are saying that union find operation, right? Connected.
Yeah.
I mean that operation can be either is connected or union, any kind of operation.
Okay. Sure.
Right. Basically, see what we have seen, right? Either so you are gonna ask couple of questions to your data structure union find, right? So let me get that. Which one it is?
Topic.
Was it in the beginning?
Yeah, it seems.
Yeah, it is connected or not. Union both. And find basically it is internally used. I am not sure if you need externally, but it's fine, right? So connected and union are both two main call that you're gonna use, right? Main operation, and each operation take O of one time, or you can say the log star m. Okay, to be very accurate. So if you are doing m operation can be either it can be either connected or union or combination of both. It is gonna take m into log n time.
Okay. Yeah.
Okay. So yeah, complexity we changed to log star n for one operation. Now, if you are doing n operation, it will be n into log star n.
Okay.
Or m operation. Okay.
Okay.
Any other question for this?
You see, it would it be useful to see, you know, how many children a subtree have? Like, you know, in this case, we have rank right here. At any time, we can say, okay, this node have how many children under that?
Yes.
And what would be the application for that?
Or to say how many children under it?
Yeah.
What would the application? So one is that we need that numbers to basically you are talking about weight that we maintain, right?
Right.
So for our algorithm, we need that weight, right? For yes. Our algorithm to be
we do need it, but outside, you know, would that be useful information?
Yes, there are some problem. It will be useful. For example, you want to find the biggest island. Right. You find all the island.
Yeah.
You want to which one is the biggest one?
Yeah. Yeah. Right.
Something like that. Okay. Or there are some problem. You know, I haven't put in my list right now, but there are some problem that basically, you know, take in consideration the size of connected component.
Yeah, Bhavesh.
I'll try to find that problem when we discuss next.
Bhavesh, like we are already at like 11:15.
Okay.
And I just want to ask, like, do you want to continue this session next Sunday and maybe take like 2 or 3 different problems, different kind of problems that we can solve using Union Find?
Yeah. I'm just answering any question with whatever we have discussed just now. But yes, we are not going to solve this today. Anything?
No, like, but is that a plan? Like to do it like next Sunday?
Yeah. Okay. Yeah.
Thank you.
Okay.
Yeah.
So
thanks, man.
Yeah. Thanks, Bhavesh.
Thank you, Bhavesh. Right. Yeah. Thank you. It was a great session. Yeah. Thank you.
Thank you, Bhavesh.
Thanks, Bhavesh.